node. So now we're going to go over to a priority queue. So this is Dijkstra's algorithm. So this is, yeah. No. Well, you can do it, but it won't give you anything useful. That's what we're doing now. Right? So if you go onto Google Maps and say, give me the shortest path from where I am to where I'm going, it runs Dijkstra's algorithm. All right? So it's definitely something worth knowing. The precondition is you're given a graph, which is either directed or undirected, and every edge has a positive weight. Dijkstra's algorithm doesn't work with negative weights. There are other algorithms with negative weights, but not Dijkstra's. And a special source node, right? And what does it do? It finds the shortest weighted path, right? What's a weighted path? You got a path. Each edge has a weight, so it's the sum of the weights, right? I mean, here, think about what is the weight of an edge in Google Maps? It's sort of more an estimate of time. Right? Because you would rather go along the highway than along a little back alley, and you would rather go along a road that doesn't have a lot of traffic. Right? So the weights are going to be some approximation of time. All right. I made these slides in Africa. Not that that matters, but I like them much more than my other slides. I brought the castle in and the city. So I was very pleased with my castle slides. All right, so here, S is the queen. She lives there in her castle, right? Or the king. Maybe the king's there too, right? And they love their people, of course, and they treat them benevolently, right? And so what we want to find is the shortest path from each home to the castle, or from the castle to the home, so that they can sufficiently love each other. All right? So there's a path, right? And it's a weighted path, so the length of the path is 8. Everybody got it so far? And then what's the pi, right? For each home, pi tells you the parent. Right? So here I'm saying pi of this house moves you along this edge that gets you to here, and then pi of that edge gets you back to the castle. Right? All right. Now, why are we doing this? Because so everybody can come and go quickly and get to the ball. Right? And also, he has another motivation, is that it's the king's duty to guard all of his people. So he's going to guard these paths. All right? And but the problem is Rome wasn't built in a day, so he's going to handle nodes. And his algorithm is going to be handle nodes in terms of perceived distance from S. Right? He might not know the perfect distance from S, but he's going to have some sense of its distance, and that's the order in which we're going to handle them. All right? And so, just like we did with the Great Wall of China, we're going to put a wall around the guys that have been handled. All right? So, what's true about handled nodes? They're in the wall, and their neighbors have been found. The neighbors have been handled, right? The edges have been handled. The neighbors have been found. So what is our loop invariant? Yeah. So the loop invariant is anybody that's handled, any place that's handled, we know the answer. All right? Capital DU tells you the length of the shortest path to the node, and the pi of u tells you the path back to the castle. All right? So if you're in the castle walls, we've solved the problem. Right? But more than that, right? Oh, and when do we done to get the postcondition? Well, if all the nodes are handled, then this loop invariant tells us that we have the answer. Right? We're done. Right? So because let's have a knight protecting people, right? Any node, an edge is going to be guarded when it's a handled edge, right? So this node here, it's a handled node, and so this edge is coming out of a handled node, so it's been handled, right? So this is guarded. So everybody follow that? This node here is not handled, but the road to it is handled. So what we have is that an edge, we define an edge to be handled if it's coming out of a handled node, right? Because when you handle a node, you handle the edges coming out of it, right? And the guard is protecting those. All right, so all edges. All right, what are the edges that are handled? All the edges in the within the wall are handled, right? And which other ones are handled? What about this guy here? Is it handled? Yeah, he has a knight here, right? Because this node was handled. So this one edge leaving that is handled. All right? So what we're doing is, if this is the wall, and there's a node here that's handled, then that edge is handled, right? But also that edge is handled. Well, if this is a directed edge, then this edge, this guy was handled, so we handled all the edges leaving it. Right? Everybody good with that? So we have a definition of handled nodes are the guys inside, and for them we have the right answer. And the edges leaving the handled nodes are handled edges, right? And they're guarded by our knights, right? And this guy here is guarded, right? So now we want to talk about so the unhandled edges. Let's talk about unhandled. This edge here, is it handled? No, so it's not guarded. And so it may have burglars along it. Right? Everybody with me here? All right, so now we need to define a handled path. Right? What's the definition of a handled path? It goes along handled edges. Right? Pretty straightforward, right? Handled edges. And what do our handled edges look like? Our handled paths. Right? They start at the king, and it follows handled edges. So is this a handled path, this path here? Yeah, because the path, what's true about the path is it goes to all nodes in the walls, and then it takes one last edge leaving. Right? So handled paths do this, and then they take one last edge. Right? That's what a handled path is. Everybody with us here? Right? I.e., paths that travel from S between handled nodes within the walls, and then one last edge leaving the gate. Yeah. We're just about to go there. All right? So that's our loop invariant. And now, the unhandled nodes, right? Well, what you said is we already said it's true for in the walls. We have the best answer, and they're within the walls, right? So what about, we're going to have a pi and a d value for the people outside the walls, and what they're going to give you, right, the d value is going to be the length of the shortest handled path, all right? So, and the pi value is going to tell you who the parent is in that path to trace it back, all right? So here, this little house has this path from S to the house. So D, and if that's the shortest such path, then the D of U will tell you the length of that path, and the pi will tell you the parent back into the castle walls. Right? So here, maybe we know that this length of this path is 8, and the length of that path is 20. Right? Now, what about this guy here? Right? He's screaming, yes. Why? Because burglars, right? What's special about him? He's way out. His edges aren't handled, aren't protected, right? So what is his D value? Infinity. Infinity. Why? Why is it infinity? It's because there are no handled paths to it, right? This is not guarded, right? These are all not guarded. So there are no handled paths to it. So his D value is infinity, and his pi value, it doesn't matter what his pi is. Let's go back to what is, we want the smallest, the D value is the length of the smallest handled path. The set of handled paths is empty. So what's the minimum of the empty set? Negative infinity, right? Why? Because we're going to later improve it, right? This is a bad path, and we want to improve it. So we want it to look bad, right? Everybody good? All right, so now, right, what's this path to the barn, right? What's the length of this path? 8 plus 5 is 13, right? But it's better than this, right? Why is that? So 20, what is 20? The weight of the shortest handled path. Is this a handled path? No, right? In fact, let me tell you right now, you guys aren't doing the next test. Well, you're doing the next test, but not the next test. You're not doing a test on graph theory. And that test, I always gave the same questions, and half the people got them wrong, right? We would have some graph like this, and I would say, what's the D value of this node? And everybody would say, well, this is 8 plus 5 is 13. They would say it was 13. And then that would be wrong, right? Everybody got that? Everybody see that the shortest handled path, there's only one handled path, and it's 20. All right? So the length, this is just repeating. What's the length of the red path? It's the 8 plus the 5, which gives you 13, right? It's better than the unhandled one, but it's not guarded, right? Right? So now what we want to say here, here's our, everybody good at what we're doing so far? So now we're going to prove something. We're going to prove that if the house has the smallest D value, then its shortest path from S, its shortest path is already handled. All right? So here, that's not true for this guy. The shortest path to it is of length 13, right? But it's not handled. It's not guarded. But this guy, this little cottage, he has the smallest D value, right? 8. And so the theorem says, for the guy who has the smallest D value, the shortest path, the shortest handled path is in fact the shortest overall path, right? Does that make sense? And why? If we can prove it. Well, we prove it by little waving our hands around. Suppose there was a shorter path to it, right? Suppose that path was shorter. Well, what does that shortest path do? It wanders. So what the contradiction would be that there was a shorter path that wasn't handled, right? So if it, all right. So yeah. So if there's a shorter path, then it first wanders around through here, and then it takes at some point it has to leave the wall, right? So here's a shorter path. At some point it has to leave the wall. First place it leaves the wall, it gets to the barn, right? So the length of that path so far is handled because it's wiggling around and then it leaves. So the length of that piece is given by the d value, right? And the d value is bigger than its d value, so that's not a better path. All right? I think I muddled that a little bit. Let's try it. I'm going to say it again. All right? So what we want to prove is that the shortest path to this thing is, in fact, the handled one, i.e. this guy of length 8, right? The 8 is the shortest handled path. We want to show that it's the shortest overall path. Why is that? Well, if there was another path that wasn't handled, so this path here is not handled because it's going through this guy, but you look at the handled piece that wanders and then gets to here, right? Up to here, it's handled. So by our loop invariant, we know that this d equals 20 is the length of the shortest handled part to get here, right? But since it has it's bigger than, why is it bigger than 20? Because 20 is bigger than 8 because this was our smallest one, right? So this path here has length at least 20. Now, if this edge has length negative 1,000,000, right, then this would be a better path, but we don't have negative weights. Right? Are people buying this? Yeah? Yeah, but if this is 6, we would be talking about this. This is the node that has the smallest d value. Yeah. So not all of the. So here, if it has the smallest d value of the unhandled guys, right? The guys inside, they have capital D values because they're the right answer, right? These guys outside have baby d values. And what are the baby d values are the best handled path, right? And then we take which one has the smallest d value, and that's this one with the 8. So 20 is bigger. Well, the path, we know the purple is the best handled path, right? We have the best handled path of these. So now by contradiction, maybe there's a better path to this little cottage. But if it's leaving by a gate and going to somebody else out here, then that handled part has to have weight 20, which is already too big, right? And if it was moving around here and then leaving and going here directly, well, then it would be a handled path. So we have the best handled path, right? Everybody kind of. All right, so that's what we know. We know that this. So what are we gonna now? What do we want to do? We want to handle somebody, right? And who do we handle? The guy with the smallest d value, right? Consider the unhandled node with the smallest d value and handle it, right? So that's what we're going to do. Everybody follow that? We keep track of all these guys in a priority queue according to their d values. And we take the one with the smallest d value, right? Right? Normally, here we take the guy with the smallest d value. Normally, its d value isn't the best handled path. It's the best handled path. It might not be the best overall path. But now, because it's the smallest d value, we know it's the best handled path. And that's good because when we handle it, right? Here, let's just say they're stored in a priority queue, right? We handle it. So what's happening is we're making the wall include that house, right? And now we have to make sure we maintain our loop invariance, right? So we handle the outgoing edges. Where are we? There. That makes that guy guarded, that wall, right? This used to not be guarded. It used to be not handled, but we handle that. And what does it mean to handle it? Is we update the neighbor's d values, right? So here, the path to this house is of length 8, and now there's an edge here of length 5, and that gives us a new path of length 13, right? Everybody see we have this new, and the 13 is better than the 20, right? So we update it. So where are we updating it? Ooh, that guy's gone. We changed that to 13, and we changed his pi to be coming up here, right? He used to have a pi going that way with value 20, but this is now better. So he updates the pi to go here, and his d to be 13. Does that make sense? And now we maintain our loop invariance, right? Our loop invariance says that for the handled nodes, we have the right answer. We have the overall best path, right? And we already knew the answer for these, but this is the new handled guy, right? It's a newly handled, so its path we had to prove is an overall best path, right? Because the guys who are handled, we have the overall best path. And then, so we did that, and the unhandled nodes, it has to give the shortest handled path, right? But here's a handled path, and we've included it into our data, right? Does that make sense? And that's the entire algorithm. And that's the code for it. Yep. Oh, we're going to get to that. What's the algorithm? Okay, we start with the directed or undirected node in a special node S, and what do we return? We return the pi and the d that gives you the shortest path from S to each node. Right? Each node will have a pi and a d, and the d tells you the length of the shortest path, and the pi tells you the path going backwards. Right? And how do we do it? Well, initially, the not handled, the handled guy, not handled. All right, we can throw everybody in there, right? So initially, at d of s is 0, and we don't care who its parent is, and everybody else has a d of infinity, and we don't care who its parent is, and we haven't handled anybody. And the not handled, here, and we haven't quite covered this yet, but we put everybody in the priority queue, because I guess nobody's handled, right? So everybody's in there with their d value, right? And then what we do is the not handled is empty, then we quit. Otherwise, you take the u from not handled that has the smallest d value, and you handle it. How do you do that? For every v connected to u, what do? You calculate the newfound path. What's the length of the newfound path? It's the length from S to U plus the weight of the edge from U to V, right? And then you see if the found length is better than the current length, then we update. We update the D and we update the pi, right? And when we update its D, it needs to move where it is in the data structure, right? Because its priority has changed. Remember, the D is sort of sorting them by the priority queue is sorting them by their D, and you change the D, then that changes. And that's the entire algorithm. You move V into not handled to handled. Everybody got the algorithm? No? You got a question about the algorithm? The loop invariant? This here? Well, you take, let's do it here. All right, so here, what's our loop invariant? We have the answer for everybody in here, and these guys outside, the D gives you the shortest handled path, right? And then what we're going to do is we're going to grab the guy out of the priority queue that has the smallest D. So we're grabbing this cottage because, see, it has the smallest D. And then what we do is we handle it. By handling it, well, one, it becomes, if it's handled, it's now in the gate. But we also have to handle the edges coming out. So if this is our u and this is our v, we're going to update this d value. And so we calculate the length of this path. The length of this path is this guy's d value plus the length of this edge, right? And so that length is 13. And then we see which is better. Is the 13 better or is the 20 better, right? And the 13 is better, and hence we update that, right? We no longer consider this path to v. We now consider this path to v, right? So that's what the code is doing. Is you take some u, which is the cottage with the smallest d value, and you look at every v that's connected to it. That's the barn. And then we calculate, is there a better path to the barn? And what's the better path to the barn? It would be the path from S to U, which is its d value, plus the weight of the edge from U to V, right? So that's our new path. Then we see, is that path better than the path we have to V? And if it is, then we give BV will be the new path and the new parent. People follow that? All right. So here we're going to kind of do it again just to make sure that we've all got it. Here we have a little bit of the graph, the definition of the handled paths, right? If those nodes are handled, then which are the handled edges? Those are the handled edges, right? They go inside of the gate and one last edge leaving, right? What are the handled paths? Those are the handled paths, right? And what's our loop invariant? Our loop invariant is that the D here gives you the shortest handled path, yeah? Yeah. Here? This one? Yeah, so that's what I was about to say. Don't ask questions of the things I'm just about to say, but right here, the D value gives the inside the handled nodes we have the best D values, and for these nodes out here we have the best handled path, right? So here's a node that's not found. But we don't care it's not found. We just give it infinity, so it's still in the queue, right? And so this guy here, what's its D value? It's the length of the black guy, right? This path some path coming this way could be better, but we're not paying attention to it, right? What are the basic steps, right? We have a D value here. And then we already have the shortest handled path to here, and this is the shortest handled path to U. And then we look at this edge, and now the shortest handled path to V is either the shortest path to V from before, or it's this new updated one, right? Which is the path to V to U plus the weight of the edge. You better start typing, buddy. I keep doing it over and over again. Why? Because, yeah. Let's do this. All right, so we start with D equals 0, and then everybody else has D equals infinity. So who has the smallest D value? S. So we take S, and we handle its edges. And note that updated all the D values. Right? Now the D value, these are the only handled paths. So this one, the shortest path to D through handled guys is clearly that. And these guys are still infinity because we don't have any paths to them. Right? And then what's the smallest D value? Is A. So we update its edges, right? The shortest path here used to be 40, but now it's going to be 1 plus 30 to give you 31, right? And what about this guy? It had infinity, so it's definitely asking for improvement to 1 plus 2 to give you 3, right? Everybody buy that? And then we take the smallest d value, which is, and here, look at my colors. The black edges is the tree that we know that's the best path, right? It's the edges, it's the path to the handle guys. These are completely inside of the castle. And the brown ones, or orange ones, whatever that color is, are the ones going from handled to unhandled. They're the ones leaving the walls, right? And the yellow edges, I guess this one's yellow, but that's because we're ignoring it. Yeah, they're either uncharted or abandoned, right? This edge here is uncharted, but this edge here is abandoned. Because it was 40 and we found a better path. Right? So now when we handle this, well, this to here is of length 3 plus 15 gives you 18, which is better. Right? And here 3 plus 1 is 4, which is better than infinity. Right? So we update those guys. Right? And since he's handled, we have the best path. Right? The 18, we don't know it's the best path. It's just the best handled path. But here, the d equals 3, we know is the best path. So then we look at the next d, which is 4, right? And we update it, right? 4 to here is 4, plus 1 is 5, so that's better than the 18, right? So we update. We update both the d value and the pi value of d. D's d value is now 5, and its pi is now g. Right? Everybody buy that? And then that's the next one. So it updates there, down to that. And that's the next one. And so what is it going to... So this is 6 to here plus 3, right? Oh, plus 3 gives you 9, and that's better than this. Right? So that gets updated. And then the next d value is 7. And 7 plus 8 is 15, which is better than infinity. 7 plus 1 is 8, which is better than that, right? So those both get updated. People following this, right? The smallest d value is 8, which updates, right? This here is in the wrong, right? So then we keep moving. And then now we can actually even keep going here. This is infinity. Infinity plus 3 is infinity, right? So that wasn't very excited. And we're done. Everybody got the algorithm? Dijkstra's algorithm. And now what's the running time? Any questions about the algorithm? What's the running time? Well, again, every edge gets visited twice, right? But this update rule, right, you have to think, what's the time to do this update? Well, that's not very big. You just add and take the minimum and move it over. But when you update the d, what happens? The d gets smaller, and so it's going to move in the priority queue. Remember, what data structure do we use for priority queues? Heaps. Excellent. And so we're going to move, it's going to move up in the priority queue, right? And what's the depth of the the heap? Is log n. So every operation takes log n time, and so our algorithm is the number of edges times log n. Yeah, people kind of buy that? It's the number of, for every edge, you have to update the heap, right? And how do you update the heap, right? Here we have our heap. The minimum is up here, and some big number is here, right? You bubble it up. You compare it to its parent, and you swap if it's better. And you bubble it up. It takes you log n time. Yeah. Because if it's directed, I only do it once. If it's undirected, I do it twice. Any other questions? Yeah, it finds for every node the shortest weighted path. Oh, look at this is the question I put on everybody's tests and they get wrong. All right? So I give them this picture and I tell people, give me the D values. And we're searching from A. So what's the D of A? You know, we got 0 and we got 13 and we got 16, which is this way, right? So those all have the optimal paths. What's the D value, right? This guy here, 16 plus 1 is 17, right? 15, right? That guy is 17. This guy here, right? Well, this is 16 plus 4. That, go this way, you get 17 plus 2 is only 19, right? So is the answer 19? Or is the answer 20? How many people say 19? How many people say 20? The 20s are right. Why? Because this is not a handled path. Right? That's where everybody was getting it wrong. I told you you'd get it wrong, and you did get it wrong. Right? Everybody got that now? The shortest handled path is the 6 plus the 4 to give you 20. Right? Because the 13 plus the 8 is bigger. But this path is better, but it's not handled. Right? So then, what do you do? Then I say do one step, and what do? Is you have to handle C. And when you handle C, what do? You make it into the picture, and then you update this, which gets updated to the D is 19, and it's the pi of E is C. Yeah, they had to do this on the test. And yes? No, D's E. E is the number of edges. You give me a graph, I count the number of edges. Number of edges in the input. Yeah, no, that's the main thing. It's the number of edges in the input. All right, so people are wrestling. Are we running out of time? Excellent. I got 2 minutes. Everybody wrestles 2 minutes. Gives me that 2-minute wrestle warning. So you're not going to have this test in this time around, but it could be on the exam, right? And here we're doing heaps, and so we can talk about. Maybe we can even do it right here. I got a full 1 minute, right? So what are we doing here? We're just saying that we have a heap, and you have to have pointers from here back to the heap so that you can find things, right? And then you bubble them up. And here we compare those two, and it bubbles up and make it into a heap. And you have to, as you bubble it, you have to change the pointers back and forth. And that's what we're doing. And also, here's our data structure is when here the outside world has pointers in and out of the data structure, right? And here's just some other traces of Dijkstra's. And now we're done Dijkstra. Excellent.